Hello, everyone. It's my pleasure to give a talk in today's workshop. And as Andy mentioned, today I'm going to focus on the theory and methodology of adiabatic relaxation dispersion experiment, as well as a new type of data analysis tool called geometric approximation. And then I will mention the complexity of conformational dynamic we might face in our research. And then I try to show you some example how to implement and following application of Johar on the AMI group. And then we try to implement this technique into the complex spin system CH3, then show two following applications. So I think Andy already showed this figure before, and I will just briefly go through, and also based on what other people's question, I will just talk about some part of it, focus on part of it. Okay, so for adiabatic R1 row experiment, so we start the meditation aligned in the z-axis in the laboratory frame at the beginning. Okay. Then you start to apply adiabatic pose, okay? Then you will see your minimization, your bulk minimization will follow the effective field. So sorry, I need to do something. There's the pointer. Okay, so you can see your bulk minimization should align with your effective field, okay? Very similar to the conventional R1 row experiment, the only thing different is now this effective field is not constant anymore. Okay, it's going to drive your bulk minimization to sample a different part of your spin space. Okay, then what is adiabatic R2 row? Actually, is you start with the minimization on the plane in the laboratory frame, okay? Then you start to apply adiabatic pose. So your minimization is always perpendicular to your effective field, okay? So when you project your bulk minimization onto your transverse plane in the laboratory frame, so you can see the trajectory is very sophisticated as compared to the adiabatic R1 row. But if you really want to compare it with conventional experiment, the best way to compare it with is CPNG experiment, which Andy already mentioned before. So by changing your stretching factor of the adiabatic pose. In this case, we are using hyperbolic secant. So in the equation, there's a one parameter. Basically, you can change the number. Then you basically can tune the trajectory of your bulk minimization. So the longer your bulk minimization stay on the plane, then you will incorporate more R2 rate. So all the relaxation rate you measure is not pure R1, not pure R2. They are a mixture of the R1 rate and R2 rate. Depending on what is the trajectory, and they will give you a different incorporation. So you will incorporate, sometimes you incorporate a little bit more R1 rate, and in some cases you will incorporate more R2 rate depending on the experiment you are running, and also depend on the pose you are using. So as I said before, this is the shape of adiabatic pose we are using. Here are the hyperbolic secant, and if you want to look into the detail, you can look at the McGarwood's paper. They have a detailed description of the various adiabatic pose. So we picked the hyperbolic secant is, so far we are, those are the one we are more familiar with. So in the left-hand side is basically how your adiabatic pose sweep through the different frequency. So unlike conventional experiment, you are conventional R1 row experiment, you are fixing your offset and fixing your amplitude of your RF field. Both your offset and your amplitude change constantly. So that is the shape of the pulse. So here I will show you the trajectory that will tell you the difference. Okay, so I need to leave the display mode. So for adiabatic R1 row experiment, so as I mentioned before, you start with the z-axis in the laboratory frame. They start to move. You can look at the blue line, which represent the trajectory from SH1. Most of the time, it stay on the z-axis, and then yeah. So eventually, we're going back to, this is a display error. Sorry. Issue at the end, you will go back to the original point, but the difference you can see, the amplitude of those Bochumization are different because they experience a different trajectory. They sample a different place in the three-dimensional spin space, so they have a different relaxation rate. Let's look at the adiabatic R2 row experiment. So you can see they start to go crazy, but they follow a certain rule. They are always perpendicular to effective field. But eventually, they will, okay, this is another display error. So they should align back to original point, but they will shift the phase based on our simulation. And actually that kind of phenomena we can see in our experiment. So they indicate our simulation can represent what happened in the field, our simulation can represent what happened in the experiment. So here, I show you the relaxation dispersion profile from these two types of different experiments. The left-hand side is the dispersion profile for R2 row experiment. The right-hand side are the profile for the R1 row experiment. Both of them are adiabatic version of a experiment. So we can see both experiments are sensitive to different time scale. A combination of these two different experiments allow us to sample and probe a wide range of conformational dynamics. So as I mentioned before, adiabatic R1 row experiments are very similar to conventional R1 row experiment, and adiabatic R2 row experiment actually is a adiabatic version of CPNG experiment. So why should we use these two experiments rather than conventional experiment? If we can combine the two conventional experiments, we should solve all the problem, right? But we all know in the past that there's no perfect pi pulse. Okay, even adiabatic pulse is not a perfect pi pulse. There's no pulse are perfect. Okay, so what we need to do is in the present, especially in the present of a chemical exchange, we need to minimize the effect of the pulse imperfection because that will be amplified by chemical exchange. Things will get more chaotic and more complex when you involve chemical exchange. Okay, so unlike the original concept proposed by Richard Ernest, so he developed a famous Fourier NMR spectroscopy. Now we kind of go backward. So we are sweeping the frequency except the spin one by one, okay? And we are not turning all the spin system 180 degree, and we are leading all the poles. We are leading those poles. We are leading those spin system turn 180 degree. Okay, so we are not forced them to turn, we are leading them to turn. That's the whole point, okay? So there are several other advantages over conventional experiments. So I cannot list all of them. I just give you some potential benefit of using this type of experiment. So when we try to implement this technique to a different spin system, we find out we don't need a complex proton decoupling scheme to remove famous cross correlation between CSA and the dipole-dipole interaction, and which has been a potential issue in the non-adiabatic version of spin lock experiment, which is well documented in the literature. Okay, and also it also allows us to use a more powerful and complex pulse to explore and complex conformational dynamics. So nothing is perfect. Our experiment do has its own issue. So what is the biggest challenge to using this type of experiment? Data analysis actually is the biggest issue. So we are actually need to analyze the real time-dependent Bloch-McConnell equation, okay? So you need to provide a fast, not just fast, but also accurate solution. So I propose this methodology. So it's called geometric approximation. Later, you will know what I mean approximation. Okay, so let's start with a simple two-side exchange model. So this is a Bloch-McConnell equation, and we formulate the mathematical problem first, and then we use the supercomputer to help us to compute the solution library, as Andy called lookup table. And it's huge in the math, but we need to develop a way to let the personal computer to use this useful information. And we don't need to repeat to calculate the answer, which we already know again. Okay. So once you generate the library, you can input this library into your personal computer, and MyScript allow the personal computer to approximate your solution surface in the extremely fast way. So first you need to identify the closest point in the library, and then you need to look at the nearby point that allow you to fast determine the coefficients of the polynomial function here. So here I just show you the the simplified scheme, because this is apparently showing the two-dimensional surface, but which does not make sense, because our surface actually can be as, the dimensionality of our surface can be as high as a 7 dimension, okay? And then they can allow us to approximate the solution surface using this local polynomial function, okay? So we can determine the value in a very fast and accurate way, which allow us to do the massive sampling. Here we use the research with simulating annealing. Then they can help us have a better chance to find the global minima. Okay. So this is unpublished data. So I just show you that we actually apply this technique to the CPNG in the case of the simple two-side exchange. So I do some optimization to build the library and then write the script to analyze the data. So the average error between the surface I build to the numeric simulation is only less than 0.5%, okay, in average. And then I have the algorithm to optimize the surface by itself without with little human input, and actually get a slightly better result that made me feel comfortable and feel good. So basically, the surface I generate is pretty optimized. Okay. And we also try to apply this idea to a more complex exchange model. In this case, it's linear three-side exchange model. Okay, So while, and in this case, we can see the dimensionality will be large, and the solution, the library you need to build will grow exponential. But how can you build a library which is small enough so your personal computer will not blow up? Okay. So what we do is we do the principal component decomposition, use the same concept. So we decompose this surface to 2 lower dimension solution surface and 1 higher dimension surface, and transfer most of a geometric feature to the lower dimension one. So you can use the higher grid point, higher number of grid point on the lower dimension solution surface, while you can use you can decrease the grid point in the higher dimension solution, solution surface. So the size of library can be reduced by 100,000-fold, and then we still maintain the average error from this solution surface to the true numeric integration, less than 0.5%. Okay, so we also simulate a bunch of data. We want to know whether they really work, you know. We simulate a bunch of data with different constant time from 30 milliseconds to 60 milliseconds. Oh, this is going back. Okay, and we see a pretty good alignment, meaning that when you input your dynamic parameter after you simulate the data and then analyze with your tool, you should expect the output, the parameter need to match with your input value, all right? And then, you know, we get pretty much a lot of agreement, except some of them. That is also at the same time we realize it's possible the data would, we think we put enough data, but it turns out it's possible the information contain those large amount of data is still not enough to get the accurate result for the unsight exchange model. So let me start to think about the complexity of the conformational dynamic in the biomolecules. So people tend to have some bias. Everyone has bias. Actually, more or less, you know, as we know from the basic principle of thermodynamics, there are correlated motion, uncorrelated motion, global motion, local motion, and also most important, our brain tend to connect what we want to observe to what we can observe. These two things are independent events, but that's how our brain functions. We try to connect what we want to see to what we can see, and then bring into, oh, that's what we want to know, okay? And that made me think when I was a graduate student, I learned this bias, so-called street light effect. So this police officer asked that guy, so is this the place you lose your wallet? And I said, no, I lose my wallet in the park, but you know, that's the place I can see the light. You know, this the place the light is, you know. So that's my reaction when I was undergrad, but it turned out that the bias is it can be an issue when we do a scientific study. Okay, and we know the biological process. Well, at least in the project I work with usually a complex one. You know, the more data biology collect, the more complex model they will propose. The fact is, the biological processes are complex, and that's the fact. We extract that the part of the system out, and then we analyze the isolate system, and we expect what we see is what we want to see or represent a certain biological function. So we need to avoid the potential bias. The way to avoid that is, you know, validation. Validation is essential step for essential step in the scientific method, and everyone knows it. So just want to bring up So let's go back to the question. So how are you going to analyze complex exchange phenomena when you only have a limited experimental data, or you only have a limited grant money? How are you going to tackle with that problem? So what we did is, we try to avoid to use this assumption global analysis, which a lot of people already use it. It's okay, but but we propose that if you can approximate the resonant dispersion profile of each nuclei by a simple two-side exchange event, okay, and analyze it, and then you will output some dynamic parameter. Sometimes that dynamic parameter will already tell you something you want to know, okay, by compare with the delta omega with the chemical sheet perturbation. But sometimes it doesn't, okay? So we developed a new way to proceed with this approach without making the assumption at the beginning is, okay, everything I saw represent the global motion. So that is so-called divide and conquer. When you deal with a complex problem with a limited resource, that is the way we think is the best approach. So let's start with one of the example we published in the JAX 2016. We try to implement this new technique to the AMI group and show you some demonstration. So this is a post sequence we basically get from the original post sequence proposed by from the two research group in University of Minnesota. And the only thing we modify is try to incorporate proton decoupling scheme to remove cross correlation between CSA and dipole-dipole interaction. So decoupling scheme was developed under the assumption that the isolated NH spin system, okay, apparently this assumption no longer hold if your protein are big enough and you cannot deuterate your sample, okay. But we have a new version of the experiment is going to publish soon and replace this older one, and stay tuned. And so that would be fine, this assumption with if we apply with a so-called ideal sample ubiquitin, okay? The ubiquitin is fully deuterated, and then we not using the wild type ubiquitin, we are using the ubiquitin mutant UB14, which is a very nice sample for us to validate our technique. This mutant ubiquitin is actually making the mutation on the beta 1 and beta 2 loop. And using the phage display, they are able to select this unique mutant, which only bind to a certain deubiquitinase, okay? So they call it UB14, okay? So they run a conventional experiment, CPNG R1 row experiment, so they actually see a huge RES turn in the middle of your primary sequence and the end of a primary sequence too. So we run our adiabatic restriction dispersion too, and we also see the same thing. We have the huge dispersion from Arturo experiment on the middle of the primary sequence and the end of primary sequence. And we do see a wide range of conformational dynamics using this approach. This is our first time to see using this modified method. With original adiabatic restriction dispersion experiment and a new data analysis tool, we are able to see a wide range of conformational dynamics. So how about implement this technique to a more complex spin system? So here we want to implement into the single quantum carbon want to implement into the single quantum carbon methylisation in the CH3 spin system. So I just give give you the brief overview of mesotrophy effect. That is pioneered by Vitaly Tugarinov as well as Risky. A lot of people deal with large molecule benefit with this new technique. So you can see when you run the HMQC without the middle decoupling, if you run HSQC without the middle decoupling during a chemical sheet evolution, then you will see there are 4 different lines, and the middle 2 are actually react the slowest, while the outer 2 lines react really fast. Okay, the reason why we are talking about HSQC is because we want to implement this technique to the single quantum term, not the multiple quantum term. Okay, so of course there are a lot of relaxation mechanisms we need to consider. As you know, the CH3 are a very sophisticated spin system. So first, we need to select the middle 2 one, okay, to remove. Apparently this already reported outer 2 line react much faster than the inner 2 line, and we want to get the mono-exponential decay, slowly decays methyation, so we need to select the inner 2 line. So we use this filter element, which originally proposed by Apex group, used in the method RDC. But we apply that to our system, our dispersion experiment. So if we have this filter and take out the proton pi pulse during chemical sheet evolution, then you can get this spectrum, and you basically tell us we are successfully select the middle 2 line. Okay, so something more complicated. Okay. Actually, we need to start to consider decoupling as well as a proton-proton spin flip mechanism, because there's no way you can get 100% iteration. In any case, you can only get some, you will always some residual proton in your system. And as your protein getting bigger and bigger, those external proton causing the problem. They will introduce additional relaxation rate, and that we need to consider. So instead of using the 6x6 time-dependent Bloch-Markov equation, we spent to 12x12 Bloch-Markov equation. Okay, so the mathematical problem become 4 times more complex, but actually the new algorithm is 2 or 3 times faster than the one we proposed before. Okay, so that is benefit from the data analysis approach we use. So, yeah. And another problem, if you see the literature, usually people ignore the cross correlation between CSA and the dipole-dipole interaction in the CH3 system, because CSA for carbon is small. We should ignore that. But it turned out in my paper in JAX 2019, we actually measure the cross correlation for the internal 2 line. It's not really small, because while you cancel out your cross correlation among dipole-dipole interaction, your R2 decrease, then this effect you are getting significant in some of your system or some of your method group. Okay. So we have to do it. In our JAX paper, we do not have a good way to remove that. So we do see this deviation in the phase change or slow exchange regime. But once we incorporate a single composite pi pulse, then we can basically get rid of this artifact. Okay. So now we try to apply this method drill hard experiment to 2 different biological systems. And the first one is kind of difficult one, because it's not a very stable protein. Well, actually a lot of protein in this group are not very stable for some reason. But, you know, but we do what we can do. So first of all, we are looking at the one of the membrane-associated protein called ALF1 and SF1 signaling pathway. Okay, so ALF1 is a nucleotide binding protein. Is GTP bound form is the active form, and GDP bound form is the inactive form. Okay, it's in the super RAS family. Okay, but in the active form, you will associate with SF1 and then facilitate the membrane trafficking. Okay, and we are not dealing with, at the beginning when we do the test, we are not dealing with this big system, and later on actually we do the experiment on this big system and still work. Okay, so we at the 2019 JAS paper, we actually try to use one of the domain called ZA domain to test the potential of this new technique. So unfortunately, this domain only soluble in the low concentration, 250, relatively low concentration. Okay, 250 micromolar, and we have to add salt. So this is a critical point. So without adding salt, this protein cannot be stable, and lower the temperature. So Mail is very, so actually there are a lot of barrier for people to study dynamic on this protein, okay? So we actually run the methyl Johar experiment on this sample. And we also see a really fast change up to 100,000 per second. And we also see several of them have the intermediate exchange, which are confirmed by the well-established CPNG experiment, okay? And we also see a very slow one, and also confirmed by the resonance splitting too. So the second application is the system I think Andy already mentioned. He want to study this E2 is ubiquitin conjugating enzyme, which play a very important role in the ubiquitination this system. So again, we run the experiment on this E2 enzyme, and then we see the motion, see the dynamics, and actually we also run the single quantum CPNG, and we also see the motion based on the IES term. Okay. Then when we add the G2BR, then suddenly in the CPNG relaxation dispersion profile, they all gone or within the experimental error. But using our technique, we still be able to pick out the motion in this system. And unfortunately, the K is not getting bigger, it's actually getting smaller. Then why can that happen? Your Ks value getting smaller and you don't see a bigger dispersion. And that can happen is when your population of your protein, the distribution of the population change, okay? So this is the experimental data I have for the bound form E2. So you can see this single quantum CPNG, you basically most of the so-called dispersion are within experimental error, and actually the profile, if you see the raw data, is almost like not sure whether there's a dispersion or just pure error, okay? And we can see several residue except the V25 this methyl group and the L59 this methyl group, but most of them can align in this in the same, in the ballpark of exchange rate. So that means the reduced experimental error as well as a better measurement precision are the key in our experiment too. So here are my take-home message. So first, this experiment, this new type experiment combined with this new type of data analysis approach can allow us for a wide range of conformational dynamics, and also can we take a different approach than the conventional one, like we do the site-specific data analysis. So we do not do the grouping. So can reveal complex conformation dynamics and provide site-specific information. And again, the reduce the experimental error allow to probe conformational dynamics with smaller RES term. If you have a large RES term, to be honest, it doesn't matter what technique you are using. If you are a huge RES term, you can even use the CPNG or R1 row or whatever technique, you will see it for sure. But the problem is when your RES term getting smaller as compared to your intrinsic R2 rate, and that will be the problem if you have a large systematic experimental error or measurement error or whatever error you call, that will be a problem. So, and our experiments are designed to perform the best in the highest magnetic field. And its bandwidth can cover if you have a 1.2 or 1.6 gigahertz in the future if you have, okay? So here I want to thank Andy. He let me to explore this, I think it's a good technique, and you know, otherwise, if without his generous permission, I would not be able to make it. And also a lot of people in the group help me prepare some sample and give me advice. Ian, we're going to give you some practical aspect of this experiment. So finally, I want to thank Shimasho, the team leader, and the senior scientist, Gabriel, for giving me, allow me to join this wonderful team. Thank you.
Thank you, Frank. That was wonderful. So the floor is open for questions. You can either indicate you have a question by clicking the raise hand button, or you can type a message in the group chat. While we're waiting, Frank, I have a couple of questions. Can you give us some idea of how fine how many points there were in the grid that you sampled on the supercomputer? What kind of computational cost was involved? I also gather that you're using a uniform mesh in all the dimensions.
Yeah. Okay, let me see. Let's go back to this. So, so the question is, yeah, I think it depends on the question you are asking. If it all depends on the dimensionality of the solution surface. If it's low, like the CPNG, the one I deal with, well, of course, I assume the intrinsic R2 are the same for both state. And in the simple case, I only need to, I can compute the library within 1 day using a 90 core of a cluster. But even the biggest one I compute, the library I need to compute is for the method Johar. That one, it took me like 1 or 2 months with 128 core of cluster. I can finish the computation. So, but once you finish the computation, I mean, this is not the big issue. You can repeat to use the library. Yeah.
So I'm curious about two things. What, have you explored GPU optimization for this? Because if you're
No,
on a
no,
12
I don't use the GPU. So one thing I want to mention, I am not a professional coder, so I don't know those fancy stuff. But all I did is I use some mathematical trick to make it faster. So I just use the CPU. Okay, I only use the CPU to do the computation. So if you do some calculation, then you will find for like a dimensionality like 7, you need to calculate the point you need to calculate huge, and there's no way you can compute it with even biggest supercomputer in the world, like within a few years. It's not possible. So you have to do some reduce dimensionality, or as I mentioned before, you can you can separate your solution surface to a different one, and then transfer your geometric feature to some of the lower dimensional solution surface. Then you can cut the number of points you need to calculate significantly.
So a couple of interesting lines that might be worth pursuing would be to explore doing the solutions in MATLAB, where you could take advantage of not only of the state-of-the-art solvers that are there, but also GPU acceleration. The other thing that might be worth considering is stepping away from the uniform grid and using an irregular mesh rather than a regular mesh. I mean, it's well known that for numerical quadrature in general, that you can get much faster convergence with an irregular mesh. So using a smaller number of samples. So, and particularly for highly dimensional surfaces, the gains can be very dramatic.
Yeah, that point I also
moving off a regular
so that's
mesh.
why. So there's another point is my axis is not always linear. Okay, some of them are actually convert to the log term, and so they made the grid point much more wider, and it's not uniform distributed.
Ah, okay.
So it's not, so you need to play some mathematical trick. It's not just, I didn't know, don't, if you go with the brute force approach, then you will get tracked and never be able to compute those libraries. So I actually do a lot of thinking then, yeah, so yeah. I mean, of course, as you recommend, if someone has a different expertise, I am willing to, collaborate or to expand it. So, yeah.
Frank, let me add one thing to that, and then I see Alexander has a question, just really quick, so that people don't get the wrong impression. The user doesn't have to compute these surfaces. One of the things that Frank did was we computed these, and that's why I call them lookup surfaces. So the surfaces are at nmrbox, and the analysis software, the things that Ian will show you in the next part, is that once the surfaces are computed once, that's all they have to be. And then the interpretation uses the same surfaces. So even though it can be made a lot faster, which is really a cool thing, I think that is useful to explore different shapes and different concepts. Whereas, the sort of two-site or the approach to three-site, the way we've done this, once those libraries are computed, it only has to be done once. So even if it's slow, it's slow, but it's only slow once. Right. And then anyone analyzing data just uses the same libraries.
Right. Alexander, do you have a question? You want to unmute your microphone?
Oh, yes. I have a somewhat might be naive and general question. You mentioned that it's important to have a per deuterated protein sample for those experiments. So what happens if it's actually fully protonated? Does it make the analysis lead to incorrect kx or delta omega values, or it's just the issue of signal to noise?
Okay, that's a great question. It depends on the so it all depends on what is the experiment you are running. So now the most mature one is the method experiment. In that case, I mean, of course, for the best method-choice effect, you need the deuteration, right? And we did it without full deuteration, and that should not be a problem, because we also consider the case that when you have the you do have the external proton. Okay, so that's why I introduced this additional term in our calculation. But in the AMI one, we are develop a new post sequence to correct that problem when we publish in the 2016. Yeah.
But so what is if you don't? So what kind of effect do remote protons have?
You mean the AMI? For the AMI, then
Yeah, for either.
suggest you don't do it. Yeah. If you cannot do it on the small protein and the fully deuterated, don't do it. Yeah, because you will get a artificial dispersion profile.
Okay.
Yeah.
So I think what happens is as the molecule gets bigger, which is where you want to deuterate, the effects get worse, right? So if you can't deuterate a medium to large size protein, then you're going to have trouble.
Okay, I see. And that means you get artificial, some kind of artifacts that lead to incorrect parameters that you extract.
Yeah,
right?
the relaxation decays are not going to be clean the way they should be.
Okay. All right, thank you.
Okay, if there are no further questions, we'll take another bio break and we'll reconvene. Let's reconvene in about 10 minutes, a little bit past 5 minutes past the hour. Thank you, Frank.
Thank you.